So, what I have already described in terms of actual sketch, I am presenting now from the textbooks. These were the lithological contacts between P and Q and between Q and R. Textbook says that find a point D so that AD equal to DB, and for that the textbook uses the two set squares and do a trial and error to locate D. I do not agree with this process. The reason is, using set square you can get approximate result, and when we have the accurate way of doing, and that too fast, I will go for that. I would join AB, that is what I did in my drawing, found out this angle, and from A I drew the same angle. So, if this is theta, that angle is theta, where this line intersects the lithological contact is itself point D. That is what I have done in my sketch. Then we finally produced the fold. The lithology Q has been drawn as folded layer, and this defines a deep domain. We can call it deep domain A, but the point A, but the letter A has already been used here. So, I would not recommend using A. Let us say call it deep domain alpha, and here is another deep domain. B has been used in the book, whereas B is already a point. So, I will not recommend using B. I will call it deep domain, say beta. The domain boundary line in this case is the axial surface, and in our drawing we took these two angles to be equal. We drew the bisector. When these two angles are equal, essentially these two angles are equal, theta 1 equal to theta 2. Basically the same thing is stated in a different way. So, this was the case with 3 lithologies and 2 lithological contacts. Now, one can increase the complexity of the problem, where there are lithologies P, Q, R, S and T, and then there are lithological contacts here, here, here and over there. What do we observe? The lithological contacts between P and Q, between Q and R, and between R and S have same dip direction, and that is this direction, say m degree north, whereas the contact between S and T has opposite dip direction. What comes out in such a drawing is that there are axial traces, and as one goes up towards the ground surface, the axial trace bifurcates, and here actually the axial traces join. So, it is a complicated realistic folding pattern, where again we are creating kink folds or chevron folds, straight limb and sharp hinges. The deep domains can be pointed out. Within these two axial traces, all the layers dipping with the same amount and in the same direction. So, this is a single deep domain. Similarly, this is another deep domain, this is another deep domain, and this is yet another deep domain. So, how many deep domains are thought about here? Deep domain 1, 2, 3 and 4. Here how many deep domains we considered? 2 deep domains. So, in case of kink method, the deep domains are straight, that is why we call it straight deep domain method. There can be more than 2 deep domains if there are more than 2 lithological contacts. The point on the axial trace where the axial trace bifurcates can be called branch point. This point can also be called as the branch point, because if I am moving from top to bottom, from here the axial trace bifurcates. Alternately, one can call this point also as converging point, since as we go from bottom towards top, the two axial traces merge. In such a case, from bottom towards top the fold geometry changes. In case of fault propagation fold, we have seen a similar case where the fold geometry changes from the core of the folds upward. We can also say in one way of thinking that this is a kind of a box fold, a fold with two hinge points, but as we go downward we do not find box fold, we find kink or the chevron fold. Where box fold has been found, within the same level if we check, we also find kink fold. So, it is not that within this level if we find box fold it will persist horizontally, it does not happen so. I have demonstrated in case of Basque method how to extrapolate the fold when there are 2 lithological contacts and 3 lithological units. From there we move to 3 lithological contacts and 4 lithological units. Now, in this case I am requesting the students to draw this situation, draw the ground surface and then take these lithological contacts. The deep amount here is least, the deep amount here is more, they have the same deep direction, and then here the deep amount is highest and here the deep direction is opposite. Create such a situation in your copy and then try to generate this fold. This fold itself can guide you how to generate the final geometry. Let us look at an interesting relation. Consider a kink fold, that means a fold with straight limb and sharp hinge, and the left limb, this one is thicker than that limb. Let us say this is limb A and that is limb B. We write that a kink fold with limb A thicker than limb B, and we have drawn the axial trace passing through the hinge points of the top and the bottom layer of the fold. We can drop normal from here and normal from this point and create two right angled triangle. This is the right angle triangle ABC and that is the right angle triangle ACD. Within the right angle triangle ABC, where angle ABC is equal to 90 degree, we can write sin alpha 1. What is alpha 1? Alpha 1 is this angle, the angle between the axial trace and this limb. Sin of that is equal to T1 divided by AC length. Here T1 is the thickness of the limb or true thickness or the orthogonal thickness. This is T1 and that is constant. Now, we are going to take triangle ADC, where angle ADC is equal to 90 degrees. There the angle alpha 2 has been defined. What is alpha 2? The angle between axial trace and this surface. We can write sin alpha 2 is equal to DC divided by the AC length. Now, DC is the orthogonal thickness T2. Therefore, sin alpha 2 is equal to T2 by AC. If I equate AC from these two equations, this is coming from limb A, this one is coming from limb B, then we can find out T1 divided by T2, that means the ratio of the orthogonal thicknesses, is equal to sin alpha 1 divided by sin alpha 2. This is an important relation. When T1 is equal to T2, for T1 equal to T2, from this relation we can say alpha 1 equal to alpha 2. That means when the axial trace bisects the angle and it is a kink fold, in that case the orthogonal thicknesses T1 and T2 are to be the same. This is demonstrated here. For T1 equal to T2, for a kink fold the axial trace bisects the total angle, therefore, theta 1 is equal to theta 2, these two angles, or in other words alpha 1 is equal to alpha 2. Remember this drawing where these two angles were taken equal in my sketch, leading to the situation theta 1 is equal to theta 2. This situation has been described as the equal angle rule alpha 1 equal to alpha 2 for parallel folds for constant bed thickness. The thickness in this limb and the thickness in that limb are the same. This is a case where the Kink method has been applied to extrapolate the fold geometry, where we were given a scale, we were given a geographic direction m degree north, we were given the tadpoles showing us the dip direction, these are the tadpoles and this give us the dip direction. Since the dip is in this direction, the dip here, there in that direction, here it is steeper dip, it is a gentler dip here. So, finally, this construction has been made. Here this is the branch point, here is again another branch point, equal angle has been maintained, gamma 1 equal to gamma 2. In this way, after the fold is constructed, a drilling well can be considered where to set up. What is described here as gamma 1 gamma 2 is basically alpha 1 alpha 2 in my previous diagram, alpha 1 and alpha 2. To maintain the constant layer thickness on both limbs, that means this thickness here and the thickness here are the same. To do that, gamma 1 equal to gamma 2 has been maintained. Everywhere the tadpole information has been followed. You see, if this is the dip direction and the dip amount indicated, then here the layer has to run parallel to the local information. Here that is the dip direction and the dip amount is stated. So, therefore, the layer has to go like this. Here the dip amount is almost 90 degree, that is why almost vertical layer has been drawn. To create such a diagram, there can be several trials made. There can be errors. So, by trial and error method, such diagram can be constructed. Here comes an important point. Even if on the surface you are getting an idea that there can be curve folded layers and not the kink layers, you can think this curve layer in terms of several short straight lines, which means that where the busk method might be applied, you can force a kink method, and after the fold is being constructed, all these segments of straight lines can be smoothened by you using a continuous curve. So, which means that the kink method is more versatile. The converse statement is not correct, where you are getting clear indication on the surface that there are chevron folds, or the geophysicist has given an information that there is rampant flat geometry at subsurface. You cannot create by busk method smooth folds and then break the smooth fold into straight line segment. This is not permitted.